This is a video that's going to demonstrate how to go from utility maximization to finding an individual consumer's demand functions for goods. And we're going to take an example that includes a particular kind of utility function that's very popular in economic analysis, in part because it's so easy to deal with. So here's the setup for the problem. We want to maximize a consumer's utility, and we're going to choose a specific function here, an exponential utility function, where utility equals a constant A times the amount of spaghetti raised to the power alpha times the amount of tacos raised to the power beta. And we want to maximize utility subject to an income constraint that says that income is spent on the two goods. PS S plus PT T. Now we know from the previous video that the way to set that problem up for solution is to use the Lagrangian theorem. And so to do that, we'll create a new variable to maximize called U star. And that's going to be equal to U, which is A S to the alpha T to the beta minus the Lagrangian multiplier lambda times the income constraint written in such a way that it's equal to 0. And so we want to take the derivative of this function with respect to each of the variables, S, T, and the Lagrangian multiplier, lambda, and set those three equal to 0, those three partial derivatives equal to 0. And so what we have here is alpha times S to the alpha minus 1, T to the beta, plus lambda PS, and proceeding along, partial derivative of U star with respect to tacos will be beta times S to the alpha T to the beta minus 1 plus lambda times PT. And then when we take the derivative of U star with respect to lambda, we know that we just get the budget constraint, which will be I minus PSS minus PTT, and these expressions are all set equal to 0 because we want to find the maximum amount of utility. So we can write these equations. Let's write an equation 1 prime here, which says that alpha times U over S. Notice that this expression here is equal to U except for this S to the minus 1 here. In other words, this is equal to utility U divided by S, and that's what we have down here. And this is equal to minus lambda times PS. And we have a second equation figuring similarly here. This is U, this is beta U over T, and that wants to be equal to, equal to minus lambda PT. So in both cases, let's make a little room here, minus lambda is equal to alpha U over S divided by PS from equation 1 prime, and lambda here is equal to beta U over S divided by the price by T, divided by the price of tacos. So two things equal to the same thing are equal to each other. So we find that alpha U divided by PSS is equal to beta U divided by PTT, and we can see that the U's on both sides of the equation will cancel out, and so we can solve for T as a function of S. So T is equal to beta over alpha times PS over PT times S. Now the next step is to substitute this expression for T in the income constraint. So the income constraint I is equal to PSS plus PT times T, but we know T is equal to beta over alpha times PS over PT times S. And now we can start simplifying expressions. And what we'll find in the end, we can for example, we can see that this PT cancels with this PT, and we can factor out PS times S from both expressions. So now, keeping the green color, we'll say that I is equal to PSS times alpha plus beta over alpha. And we can rewrite this to solve for S, which will be the amount of S the consumer wants to buy as a function of income, prices, and the taste parameters alpha and beta. So we can see that S, the consumer's demand, is equal to alpha over alpha plus beta times income times price to the minus 1. This is the consumer's demand function for spaghetti. And there's a similar demand function for tacos that we'll let you find on your own. This is price of spaghetti here. Take a look at this for a minute. What's the elasticity of demand with respect to income? Well, we can see that this is an exponential function in income and the price of spaghetti, so the exponents are going to be the elasticities. So the income elasticity of demand is 1. That's the exponent on income. And the price elasticity of demand is equal to minus 1. That's this number right here. So demand has unitary elasticity when this utility function up here is the consumer's utility function. Notice that demand depends only on income and the good's own price. It doesn't depend on the price of tacos. which is a very unusual and special case. So complete the problem by finding the demand function for tacos that will look similar to this, and you can find the corresponding elasticities of income elasticity of demand and own price elasticity of demand.